or I would even say rediscover some of those concepts from pre-calc before you can understand the calculus components of it. All right. So just a quick refresher. Oh, by the way, this is a two-part lesson today and tomorrow, and then that's pretty much the unit, all right, in terms of instruction. But that's not really a surprise because if you think about every unit in this course, it's been like a couple of days of instruction, maybe a couple of mini lessons here and there, and then a lot of time to practice. All right. So the power of -1 is a way of representing an opposite operation. So if you were to raise something to a power of -1, you're talking about a reciprocal. But in this case, it's notation representing the inverse of the cosine function. So not 1 over cosine, but the arc cosine. All right, same idea for the inverse sine. All right, so it does not mean that inverse cosine or arc cosine is the same as secant. This is a completely new function. All right, and this also applies to tangent, inverse tangent, and so on. All right. What we're going to do is explore the graphs and see how that correlates to the domain and range, and then we'll get into some calculator functions today. But then tomorrow we'll get into the calculus. All right. So start off with the graph of a cosine function. We're going to do it on the interval of 0 to 2 pi. So it's labeled on the interval of 0 to pi. So I'll just chuck in the 2 pi there. The max and min for the cosine function is 1 and -1. All right, so I'm just going to kind of arbitrarily establish where 1 and -1 will be. Cosine function starts off at its maximum. All right, then it hits the midline at the quarter-way point, the minimum at the halfway point, midline at the three-quarter-way point, and then back to the max. Oh yeah, that's a nice shaky line. All right, we're also going to jot down some coordinates. So on the interval of 0 to 2 pi, we have coordinates of 0, 1. Then we have pi over 2 comma 0. Then we have pi comma -1. Then we have 3 pi over 2 comma 0. And then 2 pi comma +1. All right. Now when you're plotting an inverse, what you're going to do is just swap the coordinates. X's become y's, y's become x's. All right. So instead of plotting 0, 1, I'm going to plot 1, 0. So just like on the last graph, I had to decide where 1 and -1 were going to go. I'm going to do that on this graph as well. So I'll put the 1 here and the -1 here. So 1, 0 would be at this location if it decides it wants to plot for me. There we go. All right, so that's 1, 0. Then pi over 2 comma 0 becomes 0 comma pi over 2. Which would go right there. I'll label them all in a sec. Then pi comma -1 becomes -1 comma pi. All right, so far I've plotted this, this, and this. So I'm going to just chuck in the labels. So this is 1 comma 0, pi over 2, 0 comma pi over 2. And then we have -1 comma pi. All right. Now, you can see I didn't really leave myself much more room to plot any more points. All right, so I'm just going to sketch this in. All right, and again, that corresponds with this portion of the cosine wave. Now, if I were to go further, what would happen is the graph would loop back upon itself. So I'll just kind of hand wave around that. So if I plotted 3 pi over 2, comma 0, that would plot right here on the y-axis at 0, comma 3 pi over 2. So this graph would loop back upon itself, all right? Which would cause it to fail the vertical line test, which would make it not a function, right? So we're only concerned with graphs that are functions. By the way, a little, I'll call it a typo, formatting issue here. It looks like it's a little shunted down there. That could be cleaned up a little bit. All right, so yeah, we want to stop here at pi, because if I go any further, then it's going to cause it, even if it loops back just a smidge, it's still looping back. And at any point, if it loops back upon itself, it would fail the vertical line test and not be a function anymore. Right? So we need functions that are basically things that are predictable. All right, an input leading to a single output.
How do you know to make that like an Assange Ventures curve there if it's like a straight line?
Because yeah. So
just like know that it's a cosine. You see what I'm saying with the ventures here, because you got the S kind of going.
Yeah.
Yeah. Okay. Good.
Yeah. So when you're looking at an inverse, it's kind of hard to really demonstrate this. I have a transparency somewhere, but what you really want to visualize is what would happen if you turn your head on its side and look through the paper the other way. That's what the graph would look like. I saw our lightsaber at Disney in the launch bay. It's so cool.
Yeah, they sell. You have to buy 2 of them.
Yeah, and
which is ridiculous.
Yeah, it's double the price.
I mean, in the mall one, like, why would anybody buy half of that? That's just.
Yeah, so we bought the whole thing.
Also, I found a website from Singapore, the only one I've ever found, that sells a NeoPixel Benzo lightsaber.
Oh,
As in the silver version you see for a second before it turns into the crossguard.
Right.
And it's the only model I've found like anywhere.
Huh.
And it costs $500.
Of course it does.
Ridiculous.
Right.
But I mean, that's like how much you pay for screen actors, reflex and stuff like that.
Right.
So it was pretty cool. Also didn't know, like I didn't never notice that his saber was like the same one, just lighter looking.
I didn't notice that.
Yeah, it's the same thing, it's just silver and doesn't have the crossguard. Because then apparently once you wanted to bleed it, that's when it became unstable and needed the vents. So it became the red crackling thing.
Good to know. Now I gotta research that.
Yeah.
They come up with a reason for everything. All right, so anyway, your range, if you just look at on the side, I have little notes here. Our cosine exists between 0 and pi, right? So if you're looking at the y-axis here, so specifically the y-axis, here's 0. Oop, that's not a marker. There's 0, and here's pi at this location right here. So the entirety of the graph exists between 0 and pi. Now the issue that comes into play here is that the graph needs to only exist in that interval. All right? If it exists anywhere beyond that because it's a periodic function, it would fail the vertical line test. All right? So the issue that I'm alluding to is the fact that you have an arc cosine function, but then you have an inverse cosine graph. All right, an inverse cosine graph would just be the cosine graph. You took the infinite graph that is the cosine graph, pick it up off the paper, and rotate it and flip it, and just place it on the y-axis. That would be an inverse cosine graph. All right, but an inverse or arc cosine function is only this little segment of that cosine graph because it needs to pass the vertical line test. All right, so we have to be mindful of this this range. This cosine graph has to only exist between 0 and pi. Now that corresponds with a certain region within your unit circle. And I just jot that down real quick. Here's 0, here's pi. So you're only talking about the top half. All right, so I'll just shade it in. All right, so that top half of the unit circle applies to the arc cosine graph. Now, if you remember this, pretty much every ratio is doubled up in the unit circle because cosine, for example, of pi over 6. Cosine of pi over 6 is radical 3 over 2. All right, but then so is cosine of 11 pi over 6. All right, so there's two instances within a unit circle in which you'll get, for every trig function, you'll get the same ratio. Right, so we don't need multiple ratios. We just need them to happen once. One set of positive ratios and one set of negative ratios. All right, so we've covered all possible ratios, all possible unique ratios, just by living in the interval of 0 to pi. So then the big question might be, well, okay, cool. Why not 0 to pi over 2, and then also if I want some negatives, why not pi to 3 pi over 2? The short answer is convenience. All right, if we have two adjacent intervals, then I have continuity. I have a continuous function. I wouldn't have to worry about having, if you really think about it, I could have this part of the graph and then skip over this piece, right, and then just pick up another piece over here, you know, a little curve over here. It would still be, if I use open and closed circles appropriately, it would still be a case where I pass the vertical line test, but it wouldn't be continuous anymore. So in order for calculus to work, we need continuity on our interval, right? So we need it to be the kind of graph that you could draw from beginning to end without picking your pencil up off the paper, right? So this is the way that we do that, because not only is it continuous, but it also includes the more convenient values like 0, acute angles, and things like that, all right? So, you know, kind of answering a question that nobody was really asking, but why not? All right. Now, arc secant, arc cotangent, they kind of follow the same rules. You know, if you really just think about it, and you can just kind of follow along for sine as well, because the bottom line is you have what the graph looks like ordinarily, and then you start flipping coordinates around, you would have what the inverse looks like, and then you just restrict it so that it doesn't fail the vertical line test. All right, so we're just going to focus on cosine and sine, and the other functions you're just going to, I would imagine, take it on faith that, okay, the same rules would apply. I would draw that graph, move some things around, and then I would have some relationships for my inverse graph. So a sine graph starts off at the origin, hits the maximum at the quarter wave point, then back to the midline. But this one we're going to go from negative pi to pi. So I'm going to go back the other way. So here's negative pi. I'm not going to label every coordinate because I think you probably get the idea on that. But I'll obviously say the coordinates. All right, we're going to max out at 1 and negative 1, max and min. This time I only went up 2 boxes, just felt right. All right, so negative pi 0 would become 0 negative pi. All right, if I plot 0 negative pi on my graph, well, I didn't give myself enough room for that based off the scale, so that's not going to fit. All right, next up would be negative pi over 2 comma 0. Negative pi over 2 comma negative 1. So I would need negative 1 comma negative pi over 2. Zero, 0, that's easy enough. Still going to be 0, 0. Pi over 2 comma 1 becomes 1 comma pi over 2. Then I could do again pi comma 0, which becomes 0 pi, but again, that's going to be off the grid. But more importantly, if I plot, you know, following this trend, I'll shade it in, I'm not shaded. Thank you. draw the line curve. If I were to continue the trend at pi over 2, I would have to stop there because if I go any further, then it would fail the vertical line test. All right, so that's the more important piece, not simply that I ran out of room on the graph. All right, so that's what my graph is going to look like, and you could see that this one is starting off at a minimum value of negative pi over 2 and a max value of positive pi over 2. All right. And the same relationships would hold true for the arc cosecant and arc tangent. Now, let me plot in the unit circle negative pi over 2 to pi over 2. And you can see that, again, it's two adjacent quadrants in the unit circle. So we're looking at a continuous graph, which is necessary for calculus to happen, derivatives, but also it's incorporating those convenient values, acute angles, 0, just basically all the nice numbers in the unit circle. All right. So when we're looking at example 1, well, 1 and 2, they're both unit circle related ratios. All you're really being asked to do is determine the angle that has a ratio of -1/2. All right. So I'm going to probably make this a little bit more complicated than it needs to be, at least for the first example, but just to kind of get across what the question's asking. So the result of an arc function is always an angle. All right. If I were to take the sine of both sides of this equation, so the sine of the arc sine, all right, inverses always cancel out to whatever's contained within the function. So that would become -1/2. The right-hand side becomes the sine of theta. So I'm really just being asked the sine of what angle is equal to -1/2. All right, so that's unit circle. If you know your unit circle trig, then this is not a problem. All right. If you don't, then you need some calculator hacks in order to kind of bail you out. Something to keep in mind, that domain range, depending on your perspective, is very important because the sine function, arc sine that is, only exists between -pi over 2 and pi over 2. All right, so it's possible that we could come up with negative angles here. All right, so, well, I'll just ask, off the top of your head, does anybody know in the unit circle where the sine ratio is equal to -1/2? I heard pi over 6, close.
210 degrees.
That would be, well, that would be correct, but that's not in the domain.
Is it just 30?
Well, pi over 6, 30, that's all correct to some extent, but that gets us in the first quadrant.
Which is the domain?
-30? Is that what you said?
Sure. I said it has to be in the third quadrant.
Oh, okay. I just heard what I wanted to hear then. No, it's got to be either the first or the fourth quadrant.
Isn't the first one
-30.
Yeah. It's in the
First quadrant is positive,
So then how could it be -1/2 if it's in the first group?
so it's not going to be in the first quadrant. So it's going to be in the fourth quadrant, so -30 degrees or -pi over 6. So we want to stick with radian measure where possible. All right. Just assume that those are the instructions unless you're told otherwise. Very rarely will you be told otherwise. All right. Okay. So let me break out the old calculator here and show you how you can get that on the off chance that answer didn't pop immediately into your head. All right. So little calculator technique. I just finished up my, well, not just, but a couple weeks ago, finished up my fall semester at the college. Calculus 3, bless you, and linear algebra, guys. So, yeah, those are the classes that come like a couple of years after this one. The reason I'm bringing that up is because at the end of each of those courses, I have them fill out a survey where I ask them if I taught them anything useful in terms of technology within the course. Bless you. And they said that the most useful thing that they got from my class, technology-wise, was what I'm about to show you, right? Because they were throwing away points related to right triangle, unit circle, trig on tests when they need not have thrown those points away. All right, so if you've struggled with unit circle trig, then this is your opportunity to maybe not struggle. All right, so your mode, it should be radian mode. What you're gonna do, very simple, is you're gonna type in second sine of -1/2, -0.5. All right, your calculator is gonna give you a disgusting decimal. Now, you got to understand, sometimes it's supposed to be a disgusting decimal, all right? Because sometimes it's just a really hideous, irrational number, all right?
And
But
tissues up there, sorry.
say it again.
Do you have any tissues in here?
I might be all out. Marty, can you check in that cabinet right behind you? Yeah, that one. Is there? Okay, cool. Thank you. Nicely done. All right, so sometimes your decimal is going to be disgusting, and that's okay. That's the expectation in a lot of cases. But I will say, if it's supposed to be a disgusting decimal, the question will have rounding instructions, at which point you know that you're supposed to round it and calculator's fair game. All right. If it's a unit circle related problem, the expectation is that you put your answer in exact form. All right. Since I know that I'm looking for an angle, that angle has to be some multiple of pi. All right. So what I'm going to do is assume that pi has already been multiplied by whatever the fraction is, and it gave me this as a result. So I'm going to divide out the pi. I'm going to take a look at that decimal and see if that converts to fraction form. All right, so math bracket, 1/6. We divided by a pi. We're going to correct for that now by multiplying by a pi.
Oh my god.
So -1/6 becomes -pi/6, and now we have it. All right. The proper response for that should be something like, oh, thank you. No, it should be like, oh, that would have been nice to know in algebra 2.
Yeah.
Right? Okay, so that's usually what I get. Second cosine of -√2 over 2. Disgusting decimal. Divided by pi. Not a disgusting decimal. I don't need to math practice to know it's 3/4, right? So 3/4, put the pi back in. I now know my answer is 3 pi/4. All right, the good thing about the calculator here, and it's kind of it's a weird departure from what you're used to in terms of unit circle trig. The calculator will actually help you avoid pitfalls related to domain and range, because the calculator understands the domain and range better than we do. So it will not give you an answer outside of the correct domain. So before, when we accidentally said 210 degrees, the calculator will never give you that 210 degrees. All right, so it actually ends up being one of those cases where it's like, all right, you know the unit circle, that's so great. Okay, use your calculator, because you're less likely to make a mistake if you do that. Now, these ones, it says flat out, get your answer using the calculator. So second tan, -0.3. Okay, using a calculator, I'm expecting an ugly answer. So I'm just going to round this, but for giggles, I'm going to divide it by pi and see if anything nice comes out of it. Nothing nice came out of it. So I'm going to round it to 3 significant. So it's going to be approximately -0.291. But then you get to numbers 4 and 5. There's a justification for why I'm going to do what I'm about to do, but I'll start it off by saying, well, you don't see an inverse cosecant button on your calculator, right? So don't go looking for that. What we're gonna do is find the inverse of the reciprocal function, so inverse sine, of 1 over negative 2.4. All right? So the reciprocal of the function and the reciprocal of the ratio,
Why did you divide by pi after finding?
just to see if it would clean up.
Okay.
I mean, there was no expectation that it would, but it's worth it sometimes to take a look. All right? Now, the justification, I'll save you from the algebra, but just a quick intuitive justification for why this works. It goes back to right triangle trig, right? Cosecant is the reciprocal of sine. Sine is opposite over hypotenuse. Cosecant is hypotenuse over the opposite. All right, so what this ratio is the result of taking the hypotenuse and dividing it by the opposite side of the triangle, or opposite side of the reference angle in the triangle. So all we're doing is correcting that by saying, well, I want to find the inverse sine, but in order to do that, I need to have the appropriate ratio to go along with sine. All right, the ratio that goes along with sine is not hypotenuse over opposite, it's the reciprocal of that, it's opposite over hypotenuse. All right, so just to kind of finish the thought on that, if I wanted to find something like, I started off with inverse cosecant, if I wanted to find inverse cosine from this, I would need to figure out what the adjacent side is in order to create that ratio. All right, so I'd have to do some right triangle trig in order to figure that out. Not difficult, but not necessary either. All right, so inverse sine of 1 divided by negative 2.4. You get negative I'll say negative 0.43. All right, something to be very mindful of, because you're supposed to do 1 over something when you're performing this calculation. The folks who kind of lose sight of this, what they end up doing is 1 over the inverse sine of negative 2.4. Try that in your calculator, you're going to get an error. And that's because a sine function can only exist between negative 1 and 1. So the minute I try doing inverse sine or inverse cosine of something bigger than 1 or smaller than negative 1, the calculator freezes up. All right? It does not have an intuitive understanding of what you're trying to do, so it just says, well, that's not possible, so take a walk. All right? So you got to be careful about things like that.
Wait, why didn't you divide by pi on that one?
Oh, because I knew it was going to be ugly.
Oh,
So I was like, not even going to bother. All right, so this one, inverse tangent. Instead of 3, inverse tangent of 1/3. So second tan 1/3, 0.322 approximately.